Hello everyone, I'm Henry and today I'm going to be explaining the significance of asymmetrical coupled oscillators and their applications. Understanding these kinds of problems can help model vibrational behavior on the atomic level, as Professor Klein from the University of Rochester explains. So, coupled oscillators are two or more oscillating systems that are connected together, which results in their equations of motion being dependent on each other, which cannot be solved with simple harmonic motion. As you can see in this mass spring system from library text, these masses are connected by springs and are identical, which means it is symmetrical. In this coupled pendulum system from Waves and Oscillations by Walter Fox Smith, the masses and lengths are identical, which makes this coupled system symmetrical also. The importance of coupled oscillators is that we can model complex systems that do not follow simple harmonic motion, and also we can take continuous limits for discrete systems such as a beaded string, and you can make a continuous string and derive the wave equation. As you can see from this video from Imager, this coupled pendulum is displaying chaotic motion. Over here, we have a triple mass spring system, all displaying different kinds of motion, animation courtesy of Dr. Dan Russell from Penn State. So, some important equations include the eigenvalue equation, which is related to the normal modes, and these describe the collective behavior of the system where all parts move with the same frequency, as seen in the previous slide. This equation states that if some vector being transformed by a matrix is equal to the same vector being multiplied by a constant, we can find this constant, known as the eigenvalue, by taking this determinant and setting it equal to 0. We will also ignore trivial solutions where the vector is 0. Another important equation is the solution for simple harmonic motion, which can be rewritten with just a cosine term and a phase shift that is equal to 0 when there is no initial velocity. We can do this by using the superposition principle for linear functions, and it can also be written with complex exponentials using Euler's formula. So here's the example problem that I will be solving. As you can see, this is an asymmetrical coupled oscillator since we have different masses, springs, and lengths. So the first step is to write down the equations of motion for our masses and the two forces acting on our system. The only forces are the spring and pendulum. So assuming the displacement is only in the x direction, we can just use Hooke's law for the spring. For pendulums, if we assume small angles, using the definition of sine and arc length, we can show that the restoring force of a pendulum is equal to negative mg over L times x. So one common mistake I see other students make here is the order of displacements for Hooke's law. For example, in mass 1, it is x1 minus x2. For mass 2, it is x2 minus x1, and so forth. This is just due to the direction of where we want our spring force to be pushing and pulling. The second step is to put our equations of motion in matrix form. So all I did here is I put everything on one side of the equation and I plugged in some values for our variables. Here, I put it in matrix form, and we are going to make an onslaught so that the x vector is the real part of z, which is x times e to the I omega t. So I differentiate here twice. After plugging in this substitution, we obtain the eigenvalue equation. We can see here that our eigenvalue equation is the angular frequency squared. So to find the solutions, we can set the determinant of this equal to 0. We can substitute lambda here and only consider positive frequencies to get a cubic equation that can be solved. So using a calculator, I obtain the eigenvalues, but to get to our normal mode frequencies, we need to take the square root, and now we have our normal mode shown here. Now we will solve for eigenvectors by plugging in our eigenvalues back into the original equation. It is very easy to mess up here, so what I like to do is get all of our variables in terms of x1 and then solve for our eigenvector. Since x1 is just some scalar number, in this case we can ignore it and normalize our eigenvector to magnitude 1, as shown at the bottom. We repeat this process for our other two eigenvalues and normalize them. So you might be wondering what this means. Well, the eigenvectors represent the amplitudes in which each mass moves within each normal mode. We call the first one the pendulum mode because all masses move in the same direction, like a pendulum. This one I'm calling the middle mode, where the third mass moves in the opposite direction. And the last one, it is referred to as the breathing mode because the outer two masses move in the same direction, and it looks like inhaling and exhaling. So now we are going to solve the equation of motion by using the simple harmonic solution for each normal mode. However, the full solution is a combination of the normal modes. As you can see here, it's much more complicated. Here we have constants that are dependent on the initial positions of the system, since we are assuming no initial velocities. So I graphed these solutions using Desmos. This specific example is purely in pendulum mode, where the y-axis is the displacement of each mass from equilibrium in meters, and the x-axis is time in seconds. As you can see here, they're all in phase, moving in the same direction. If we change our initial conditions, we can make the system be purely in the middle normal mode, where mass 3 is moving in the opposite direction. Here we have the system purely in breathing mode, where the second mass moves in the opposite direction with a much larger amplitude than the other two. And lastly, here we have a combination of the modes, which produces much more chaotic movement and behavior. So the applications of this include modeling waves on a string for both discrete and continuous versions. In Walter Fox-Smith's book, Waves and Oscillations, which is where I got these images, by the way, he notes that applying boundary conditions to strings to quantize the normal modes has many connections to the wave function in quantum mechanics, where we quantize energy levels for an electron. Another application is coupled LC circuits, which are used to model transmission lines. This can even be used to model the vibrational behavior of molecules such as CO2, crystalline structures, and even the benzene ring, as Smith explains. This example below is an example of the CO2. We model the bonds as springs, and it's asymmetrical because the oxygen and carbon have different masses. So as you can see, the coupling is not restricted to mass spring systems. You can have magnetic coupling, coupling between charged particles, and even electronic coupling. So thank you for watching, everyone. I hope you have learned something, and here are my references.